Okay, in this lecture we want to talk about lines and planes. So in particular we will look at lines in R2, and we'll also look at lines in R3 and R4, and we'll also look at planes. So we'll look at planes, not in R2 because that's not very interesting. R2 is itself a plane, and so to talk about a plane in R2 is only to talk about R2. But we'll talk about planes in R3 and planes in R4 and R5. So remember that a line in R2 is given by the equation ax plus by is equal to c. So remember, this is the standard form of a line, and we require that either a is not equal to 0 or b is not equal to 0. And so just this thing by itself without any other context is kind of ambiguous. So this equation means a line in R2, but this equation means a plane in R3. So we want to be a little more precise about a line in R2. So let's use proper set notation and describe this thing very carefully. So we'll let L be the line that we're talking about. So what is a line? For us, it's the set of all ordered pairs in R2. And so x comma y, and how is x and y related? It's related this way. So it's all of the ordered pairs such that ax plus by is equal to c for some fixed real numbers a, b, and c. Right, and again, a is not 0 or b is not 0. So this is a complete description of a line in R2. Again, this same description does not work in R3. So this thing describes a plane in R3. So in general, what is a plane in R3? So a plane in R3 is given by this equation, ax plus by plus cz is equal to d. And again, one of these three coefficients, a, b, or c, has to be non-zero. So again, this thing means a plane in R3. But if you go up to R4, this thing means something different. Now this thing means like, I guess, a three-dimensional hyperplane in R4. So these equations, it really does matter what space that you live in order to say what the geometric object that it represents. So a plane in R3, described carefully, it's the set of all ordered triples in R3, x, y, and z. And how are these three real numbers related? Well, ax plus by plus cz is equal to d for some a, b, c, d that live in R. So in the next slide, we just want to give a brief account of where these equations come from. Maybe, you can't define line or plane in Euclidean geometry, but we'll do our best to give like a basic Cartesian geometry definition, just so we have some footing on which to build these other representations for lines and planes using vectors. All right, where did this equation ax plus by equals c come from? We say that equation describes a line in R2, but why is that the case? Well, when you study analytic geometry or algebra 2, you might see these conic sections, I don't really know how to say it, but you can get all these different shapes just from two stacked cones, and one of them is a line. And one way that you can describe a line, even though it's undefined, maybe in the Cartesian world, you can say that a line, it's the set of all points equidistant from two fixed points. Call them P and Q. So for example, let's say in R2 you've got a point P, and then you've also got this point Q. Right? So what are all of the points equidistant from these 2 points? Right? So here's certainly one point that's equidistant from both of these, right? It's the midpoint between P and Q. And then here's another one. So here's a point on the line. The distance from this point to P is the same thing as the distance from this point to Q. Here's another point on the line. The distance from this point to P it's the same thing as the distance from this point to Q. So we use 3 tick marks to let us know these two lines are congruent. So any point on the line, if you pick any point on the line, the distance from that point to P will be the same as the distance from that point to Q. So let's just say we've got some arbitrary x comma y on the line. So we know the distance from x comma, well, let's give P and Q some names in Cartesian language, right? So we'll let P be the point A comma B, and we'll let Q be the point C comma D. So if x comma y is on the line, then that means the distance from this point x comma y to the point P. So here's the distance formula, right? Remember the old distance formula. It's the difference of the x's squared plus the difference of the y's squared, and then take the square root, right? So we know this thing is equal to the distance from x comma y to Q. So what's the distance from x comma y to Q? Well, it's the difference of the x's squared plus the difference of the y's squared, and then take the square root. So this equation, in terms of the points A, B, C, and D, the point x comma y that lives on this line is subject to this condition, right? This distance condition. So now what do? Well, you can square both sides, FOIL it out, cancel some stuff, move all the x's to one side, move all the y's to that same side, and then move everything else to the other side. So when you do that, when you square and FOIL and then redistribute, you get an equation that looks like this thing. So some number times x plus some number times y is equal to some number. So I'll just let A be this thing, this 2c minus 2a. I'll let capital B be this thing, 2d minus 2b. That's what capital B is. And then we'll let capital C be this thing, c squared plus d squared minus a squared minus b squared. So from this description, using only the word distance, we're able to see why any point on the line is subject to this type of equation. And so you can define a plane in R3 the same way. So you take 2 points in the plane and then collect all of the points in space that are equidistant from these 2 points, right? So that's going to sweep out a plane in R3 the same way these points will sweep out a line in R2. So that's where the equation of a line in R2 comes from, and that's where the equation ax plus by plus cz equals d, that's where this equation comes from for a plane in R3. We want to look at 2 forms for the equation of a line in R2. And then one of these we'll be able to extend to higher dimensions, and that's a good advantage, right? So one form will only work in R2, and the other form will work in higher dimensions. So in particular, we've got the parametric form for a line. So x, x0, and v are vectors in R2. So x, x0, and v are vectors in R2. And then t is a scalar in the real numbers. So this is the parametric form. This thing will work in R2, it'll work in R3, it'll work in R4, so on and so forth. So this form is really convenient because it'll work in all the spaces. The normal form, it's very closely related to the standard equation of a line, but this thing will only work, this is only a description for a line in R2. But anyway, these are the 2 forms that we want to look at, and we want to be able to convert from one form to the other with no problem, right? Sometimes we're given some information and we want to write down all 3 equations of a line, and knowing where to start can be good, and then once you've got a starting point, then you can get anywhere on the circle from any point on the circle, right? So that's what we want to do now. So we want to give a description and show why this form is actually a line, and show why this form is actually a line, both of them in R2.